All right, this is extra examples from sections 5.1, 5.2, and 5.3. So we're going to be looking at anything we skipped over in class from those sections. So on 5.1, if you count the pre-video and what we did in class, there was only one or two examples left at the bottom of this to work out. The first one was D part, and then E part, and that is it. So just those last two examples. The directions for this part were to find the inverse function of f and then find the domain and range of both. So if we look at D, notice they've already told us the domain of this original function because they've got that x has to be greater than or equal to 0. So we already know that that is the domain of the original function. So remember we said you would have something like f and f of x, or of x and f inverse of x, and then you would have a spot for the domain and the range. So we already know domain of the original is greater than or equal to 0. Okay, so we write this as y equals 5x squared plus 2. We're going to swap x and y just like we always do when we try to find the inverse. So this would be x equals 5y squared plus 2. To get y by itself, we would subtract over the 2 and then divide everything by 5. Now you still have a y squared, so you do need to take a square root of both sides, and normally we would write plus or minus when we write a square root. So as of right now, this is what I have. The problem with this, though, is that the domain was very specific on the original, that x had to be greater than or equal to 0. What we know is that when something's a function and this is the inverse, that their domain and ranges are swapped. So that means y has to be greater than or equal to 0 in the inverse. So we're only going to choose the positive case because of that. So f inverse of x equals the square root of x minus 2 over 5. We would probably, and this 5 is under the radical, if you wanted to rationalize that, multiply top and bottom by 5, in case WebAssign makes you rationalize. Then you would just have 5x minus 10 on top. You would have the square root of 25 on bottom, which is just 5. So this would be the completely rationalized inverse, so that you've actually gotten the radical out of the bottom. For the domain of this one, you just, since it's a square root, we set the inside greater than or equal to 0, just like we do with any square root. So we would add the 10 over and divide by 5. So it looks like on my inverse, my x has to be greater than or equal to 2, which means on the original function, the y has to be greater than or equal to 2, because that is always domain and range just get swapped. For the last example on this one, we need to do finding the inverse of this function, negative x cubed plus 2. So write it as y equals negative x cubed plus 2. We do our swap. So x equals negative y cubed plus 2. I would subtract over 2. Divide everything by negative 1. So that would actually make this negative x plus 2 equals y cubed. And we need to take a cubed root. Now, this means that my inverse function, and we don't need to write plus or minus when you take a cubed root. Remember, that's only when you're taking an even root of both sides. So this would just be the cubed root of, you could either write negative x plus 2 or you can write 2 minus x. Either way would be okay. And there's no adjustments to this one because there's no denominator, so there's no radical to rationalize. If you're dealing with x cubed, your domain is always all real numbers because you're just a polynomial. Cubed root of x is also got a domain of all real numbers. So because they're both all real numbers, the ranges are both going to also be all real numbers. So there's not much interesting about the domain here. All right, that catches us up on the 5.1. So let's move on to 5.2. There were a few examples that we did not do in class. We did all of the equations to solve, but there were a couple of the graphing ones that we did not do together. We did not do the 1/3 to the x, so I'll go ahead and do that. We did discover, though, that it looks just like 3 to the negative x, but we'll show you that graphically. So we pick, remember, our table. And since this is just an x up here, we can do negative 2 to 2. So 1/3 to the negative 2 power, we flip the whole fraction, which makes it 3. 3 squared is 9. 1/3 to the -1 power. Because of the negative exponent, we flip the whole fraction and it becomes a positive exponent. So that's just 3. Anything to the 0 power is 1. 1/3 to the first power is 1/3. And 1/3 to the second power is 1/9 because you square both top and bottom. Okay, so if we plot those, -2, 9, -1, 3, 0, 1, 1, 1/3, and 2, 1/9. Notice that we get an exponential function, but this time it's decaying, and our horizontal asymptote is the y equals 0. So there's that graph. I believe we might have had an application problem left on section 5.2. Let's scroll down and look. We did number 3 together. We did not do 4. I said you could omit it, but I'll go ahead and do it just in case you get one like this in the homework. It won't be on the test, but it says, if 10 grams of salt is added to a quantity of water, then the amount Q of T that is undissolved after T minutes is given by Q of T equals 10 times 4/5 to the T. Sketch a graph that shows the value from time of 0 to time 10. Now, T is kind of like our X, and Q of T is our Y. We're plugging in different hours. It looks our minutes, minutes. And I don't feel like I need to do every point between 0 and 10, so maybe I'll just do the evens. So if you do 10 times 4/5 to the 0, that's 10 times a 1, so that's just 10. 10 times 4/5 to the second would be 10 times 16/25. So we'll need our calculator for that one. In fact, we'll just type them in with the parentheses. So 10 times 4 divided by 5 to the second power is 6.4. So I'm just going to use my calculator from this point out. 10 times parentheses 4 divided by 5, close parentheses, to the fourth power is going to be 4.096, so let's say 4.1. 10 times 4 divided by 5 to the sixth power is going to be 2.6. 10 times parentheses 4, oops, no parentheses there. 10 times parentheses 4 divided by 5, close parentheses, raised to the eighth power is 1.7. So notice it's dissolving almost completely out at this point. And 10 times 4 divided by 5, which I typed in, sorry, 4 divided by 5 to the 10th power is 1.1. So if we wanted to graph this, we only need to graph the first quadrant over here because that is the all positives. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There's our first point. At 2, we're also at 6.4. So 6.4 is about there. At 4, we're at 4.1. At 6, we're at 2.6. At 8, we are at 1.7. And at 10, we are at 1.1. So notice this is definitely an exponential decay function since we have it's getting higher, it's going from higher to lower. And this is the graph. This is time in minutes. And this is Q of T, which is the amount undissolved of salt. So that's how you would do a graph tied to a word problem. Okay, we did example 5 in class, and I believe we also did example 6. So that, yep, that is the end of catching up on section 5.2. So the final section we need to do any catch-up problems on is 5.3. This was the section where we introduced the idea of E being a base for us, which means that it is a number. It's approximately 2.718, and it keeps going forever, just like pi. But it really stands for when we let the compounding interest problem, where we just look at the compounding portion as n keeps getting larger towards infinity. So that's where that number came from. And then, like I said, we did a couple examples. We did the graph of e to the x. We also solved an equation with e's in it, but there were a couple extra graphs we could do. So anytime you're doing with e, you're going to need your calculator. So if we're going to graph this one, this looks like it should just be an exponential function flipped upside down, but we're going to pick our -2, -1, 0, 1, and 2. So negative e to the -2, negative e to the -1, negative e to the 0, negative e to the first, and negative e to the second. Now my calculator is a little different than the one a lot of you had. I have to enter in the exponent first, then the base, and then tell it to times it by -1. It's just because it's not the best calculator in the world. So when we look at this one, I'm going to start with -2 as my exponent. I'm raising e to that power, so you know how it's written it as a power. And then there is a negative out front, so we're going to times by -1. So this is -0.14. And then we'll do e to the -1, so 1 negative, raise that as e's power, and then we're going to change the sign, so it'll be -0.34 or 37. So essentially all of these are just getting their sign changed. This would be e to the 0 is just 1, but then it becomes -1 because of the negative out front. This is 2.72, so that'll be -2.72. And e squared is 7.4. If we went around to one decimal place, that'd be -7.4. So notice when we graph this, we do just get an exponential function upside down. And there's my final point. So not the best drawing, but that is what it looks like. So negative e to the x has just been flipped upside down. 2e to the x should be a stretch, because we learned in section 3.5 that if you put a number in front that's bigger than 1, you're actually stretching your function. So let's look at what this would look like. I don't know why there's still a graph there. Okay, so we're going to do a table. So this would still be -2, -1, 0, 1, 2. And we plug it in, so e to the -2. And then we're going to double that since there's a 2 out front. So that would be 0.27. E to the -1. And then double that answer. So 0.74. E to the 0 is 1, but times 2 would be 2. So notice that's been stretched up. E to the first is 2.7, blah, blah, blah. So just E, and then times 2. So that'd be 5.4. And then E squared times 2. That'd be 14.8. So -2 is at 0.27, -1 is at 0.74, 0, 2, 1 is at 5.4, and 2 is off the chart. So notice this didn't really change too much of what's going on, except that it's going to get bigger faster, and it's still y to the 0. Okay, this one should be just a shift up 4. So if we know what our e to the x's were, which we do know that this one was 7.4, this is 2.7, that would be 1. So this is for e to the x, not e to the x plus 4. Just kind of giving you a comparison. E to the negative 1, I wanted to say was 0.35, but we'll do that one again. 0.37. And then e to the negative 2 is 0.14. So notice, to go from this graph, this is just the regular old f of x equals e to the x, to this new graph, we are just adding 4 to all the y's. You're just shifting them up. So you have your same table, and you could do this on your calculator, but I'm using a transformation here just to show that it's the same thing. I just add 4 to all of these points. Then we plot it, so negative 2, 4.14, negative 1, 4.37, 0, 5, 1, 6.7, and 2, 11.4. Notice this is the only time exponential functions don't have the x-axis as their horizontal asymptote. It's when you do a vertical shift. My horizontal asymptote now is positive 4. Okay, so then we have this one. This looks like, because the plus 4 is inside, it's probably going to be a horizontal shift. When you're doing a table and the exponent has been adjusted, so notice it's not just an x anymore, you want to make sure whatever makes that equal 0 goes in the center of your chart. This will guarantee that you get the right shape for your graph. So then pick 2 things smaller and 2 things larger. So e to the negative 6 plus 4 is e to the negative 2, which we already know the answer to that is 0.17. E to the negative 5 plus 4 is e to the negative 1, which we know is 0.37. Actually, that wasn't 0.17, it's 0.14. Sorry. Should have looked up at my chart. And then e to the negative 4 plus 4 gives me the e to the 0, which is 1. E to the negative 3 plus 4 is e to the first, which is the 2.7. And e to the negative 2 plus 4 is e squared, which is the 7.4. So if we plot these, notice the whole graph has just been shifted to the left 4. And that is that. Still has the same horizontal asymptote as the rest, except for the vertical shift. Okay, we did example 3 in class, and I believe we did example 4, so we are left with just a couple more word problems. This one says, how much money invested at a rate of 5.5% compounded continuously? There's a key word there, so that means we have to use this formula. This is the continuous compounding formula. And it's going to amount to 15,000. So that means that's our future value. Time is 4, and our rate we need to change to a decimal, so 0.055. So if we plug in what we know, 15,000 equals, we don't know p, e to the 0.055 times 4. I would go ahead and simplify that exponent. Oops, there's supposed to be 2 5s there. 0.055 times 4 is 0.22. So I'll write that down on the next line. So we're trying to solve for p, so we need to divide by this e. Remember, e is a number, so you're really just dividing by a number. So we need to divide 15,000 divided by, now I have to put in my exponent first. Most of you will have to put in your base first. See, that's now e to the 0.22, and that's 12,000, and let's round to the nearest dollar. So 12,038. Now we have to round up, not just because the decimal said to, but anytime you're dealing with solving for p, you want to make sure you overshoot the goal instead of undershoot your goal. Okay, and then there's 2 more examples in this section. This is called the law of growth or decay formula. Essentially what this says is that if you have a quantity after some time, it's equal to the initial quantity times e to the rate times time. Now the reason this might be a growth or decay depends on a couple things. It depends on if you have a positive or negative rate. There's a couple of reasons why this could change. So if R is greater than 0, you're growing, which means you're getting bigger. If R is less than 0, so if you have a negative rate, then you are decaying. So the population in 1985 in India was 766 million, and the population has been growing continuously at a rate of about 1.82% per year. So notice this is going to be a growth function because they said it's growing continuously. Assuming that this rapid growth rate continues, estimate the population in 2015. Okay, so N of T is going to equal initial population. So this is population after time, initial population, e to the 0.0182, because that is our decimal percentage now, and then times t. So the only thing I actually put in right now was the rate. We're going to put in all the other information. So our initial population was 766 million. I'm not going to write out all the zeros, but I have to remember that whatever answer I get needs to have the word million after it. And then this is e to the 0.0182, and this was from 2015 minus 1985. So that is looking at a growth of 30 years. Okay, so let's use our calculator. Actually, I'm going to do the e part first. So that was 0.0182 times 30. So that's my decimal that I'm using for my exponent. So I'm going to go ahead and use that times the 766. That's 1322. We're going to estimate. And I'm not going to round up, so I'm just going to leave it at that. But remember, this would have the word million after it. That doesn't quite make sense because millions should not have 4 digits. So what comes after millions? It's a billion. So this is actually 1.322 billion because there's more than 3 digits here in the answer. So that is how many people. So if you wanted to write all the zeros out, you could. Depends on how WebAssign would want that, whether or not you would have to do it that way. But yeah, it's quite a large population growth. And then our final example to get us caught up on all the extra examples from section 5.1 to 5.3 is example 7. So it says the radioactive tracer 51CR can be used to locate the position of the placenta in a pregnant woman. Often the tracer must be ordered from a medical laboratory if your initial units, because A sub 0 means the amount you order, and that's in microcuries, are shipped. Because of radioactive decay, the number of units that you get after the number of days it's been shipped is given by the following formula. So notice there's a negative exponent here, which means there's a decay of the substance as it travels. So my final value that I actually receive will be equal to the initial value times e to the, this looks like it's decaying at 2.49%, and times time. And our time here is in days, because if you notice they've got days written everywhere. So if 35 units are shipped, so that's our initial amount, and it takes 2 days for the tracer to arrive, so that's going to go in for our T. Approximately how many units would we have available for the test? Now, when you're doing something medical or where you have to be exact, you can't count like a partial unit. Sorry, let me get this where I can see it. So it's 0.0249, which is negative, times 2. So this is going to be my exponent, so negative 0.0498. I raise e to that power, and then I times by the 35 units we started with. Now that says 33.2. You're not going to be able to use the 0.2, so it's going to be approximately 33 units. So you've lost 2 units. If you actually needed 35 units for the test, so you actually needed that full 35, you should have ordered more. So if we need 35, what we want to know is what should they have ordered? And it has to be in the same time frame because this is for the same problem. So it's still going to be 2 days. So notice on this side, we're going to go ahead and write what that decimal was. It was negative 0.498. Oops, supposed to have another 0 in there. 0.0498. And this is 35, so we're actually dividing by the E. We're going to divide both sides by E to the negative 0.0498. So 35 divided by, go ahead and type in my exponent. You guys will probably have to type in the E first. Raise to the power and hit enter. I'm going to have to order about 37 units because you can't order 36 and you can't order 36.7. You have to round up so that you have enough. Now what you would notice is that it looks like it went up by 2 and down by 2 in both of the problems. That's because we're 1 unit removed from what's going on. The further out this traveling would have gone, the more distance you would have seen that this would have either decayed a little bit down further, and this would have needed to be bigger. So it's not always going to be add 2, subtract 2. That just happened to be how it worked in this situation. All right, so that is it for those sections. I will post this video, and then there's one more video to watch. That is the pre-video for section 5.4, and it is crucial that you watch it as well.